Welcome to this lecture on stochastic processes and queuing theory. Today, we are going to explore a fascinating topic, Markov chains as graphs. If you have ever looked at a grid of probabilities and felt completely lost, you are not alone. By the end of this video, you will understand how to turn those intimidating numbers into clear visual maps that make predicting the future behavior of a system incredibly intuitive. Let us dive right in. Before we look at any math, let us understand why we need state diagrams. Imagine you are playing a complex board game where your next move depends entirely on the roll of a die. Staring at a table of probabilities to figure out your chances of winning is difficult. But if you draw a visual map of the board, everything becomes clear. In probability, a state diagram does exactly this. It represents different states as circles, called nodes, and the possible moves between them as arrows, called directed edges. This visual approach transforms abstract mathematical systems into intuitive pictures. Now that we understand what a state diagram is, let us look at the mathematical rule for drawing one. This formula tells us exactly when to draw an arrow between two states. The symbol P sub ij represents the probability of the system moving directly from state I to state j in exactly one single step. If this probability is strictly greater than 0, it means the move is actually possible. The implication arrow tells us the visual consequence. We must draw a directed edge or an arrow starting at node I and pointing directly to node j. If the probability was 0, the move would be impossible and we simply would not draw that arrow. Let us see this rule in action with a concrete visual example. What you are looking at is a two-node state diagram. Notice the two circles labeled state 1 and state 2. These are our nodes. The arrows connecting them are the directed edges. See the arrow pointing from state 1 to state 2? That exists because the probability P12 is greater than 0. We also have arrows pointing from a state back to itself, like P11. This diagram teaches us that the system can transition between these two states or stay in its current state, mapping out every possible future move in one clear picture. This visual map we just saw leads us to an important concept called accessibility. Imagine driving in a city filled with one-way streets. You might easily drive from your house to the grocery store, but because of the one-way roads, you might not be able to take the exact same route back. In our Markov chain, we say that a destination state is accessible from a starting state if there is at least one valid path of arrows connecting them. It does not have to happen in just one jump. You can pass through multiple intermediate states. As long as every jump has a probability greater than 0, you can eventually reach that destination. Now that we understand the idea of reaching a destination, let us look at its mathematical definition. This formula defines n-step accessibility. The term P sub ij superscript n represents the probability of starting in state I and ending up in state j after exactly n steps. It is crucial to note that the superscript n is not an exponent. It is just a label telling us how many transitions have occurred. If this n-step probability is greater than 0 for any positive integer n, it means there is a real non-zero chance of making this journey. If we find even a single number of steps that makes this true, the destination state is mathematically accessible. Building on the idea of accessibility, what happens if the travel goes both ways? Returning to our city driving analogy, if you can drive to the store and also find a valid route back home, those two locations are deeply connected. In a Markov chain, when two states are mutually accessible from each other, we see they are communicating. This means the system can bounce back and forth between them indefinitely, forming a closed loop of travel. If every single state in the entire system communicates with every other state, we call the chain irreducible, meaning it cannot be broken down into smaller, isolated pieces. To represent this two-way relationship mathematically, we use a very specific notation. The symbol I represents our starting state, and J represents our destination state. The double-headed arrow between them is the mathematical shorthand for communicating states. This single symbol is powerful because it packs two separate conditions into one. It requires that a valid path exists from I to J, and it simultaneously requires that a return path exists from J back to I. If either path is missing or has a probability of 0, we cannot use this symbol. When you see this double arrow, it guarantees a two-way interactive loop. Before we move on, let us see this with a concrete example. We are given a simple weather model with two states. State 1 is a sunny day and state 2 is a rainy day. We are also given a transition probability matrix, which we will call matrix P. Our goal here is to convert this grid of numbers into a state diagram and then determine if the sunny state and the rainy state communicate with each other. We chose this approach because mapping the matrix to a visual graph will instantly show us if the weather can cycle back and forth indefinitely. Continuing with our weather model, let us analyze the rules hidden inside matrix P. The top left entry is 0.8, which is P11. This means there is an 80% chance a sunny day is followed by another sunny day. The top right entry, P12, is 0.2, meaning a 20% chance of rain after sun. The bottom row gives us P21 as 0.4 and P22 as 0.6. Because every single entry in this matrix is strictly greater than 0, we must draw arrows connecting every node to every other node, including arrows pointing back to themselves. Now let us finalize our weather model analysis. Because the probability P12 is greater than 0, we know that state 2 is accessible from state 1. Similarly, because P21 is greater than 0, state 1 is accessible from state 2. Since both directions are mathematically possible, we can confidently use our double-headed arrow notation. Our final answer is that state 1 and state 2 communicate. Physically, this means our weather system will never get permanently stuck in just one state. It will always eventually transition back and forth between sunny and rainy days. Now that we have seen a simple loop, let us examine a slightly more complex scenario involving a trap. Imagine a board game with 3 spaces, labeled State 1, State 2, and State 3. We are given a new transition matrix that dictates the exact rules of movement. Our goal is to determine if State 3 is accessible from State 1 and whether State 1 and State 3 communicate with each other. We will do this by tracing the guaranteed and impossible moves, step by step, looking for probabilities that are exactly 1 or exactly 0. Let us break down the rules of this new matrix. The first row tells us that from state 1, the only possible move is to state 2, because P12 is exactly 1. The second row shows that from state 2, you must move to state 3, because P23 is 1. But the third row is the most critical. It shows that from state 3, the only possible move is back to state 3 because P33 is 1. This makes state 3 an absorbing state. In plain English, it is a trap that you can never escape once you enter. Continuing our analysis, we need to calculate the probability of moving from state 1 to state 3. We know the system is forced to move from state 1 to state 2 on the first step, and then from state 2 to state 3 on the second step. By multiplying these guaranteed events together, we find that the two-step probability, P13 superscript 2, is exactly 1. Because this probability is greater than 0, we have mathematically proven that state 3 is absolutely accessible from state 1. You can definitely reach the trap. Finally, let us look at the reverse journey. We need to find the probability of moving from state 3 back to state 1 in any number of steps, which is P31 superscript n. Because state 3 only has an arrow pointing to itself, it is impossible to ever leave. Therefore, for any number of steps in, the probability of returning is always exactly 0. Because this return path does not exist, state 1 is not accessible from state 3. Our final answer is that state 1 and state 3 do not communicate. The system is not a closed loop. So, we have proven how to find traps and loops. This brings us to why this matters in the real world. Raw matrices are incredibly difficult for humans to interpret quickly, but state diagrams make complex systems manageable. When computer scientists design search engines, they treat the entire internet as a massive state diagram, where websites are nodes and hyperlinks are directed edges, helping them rank highly accessible pages. Biologists use these exact same graphs to model virus mutations, identifying which mutation states are traps the virus cannot escape. Visualizing probabilities is a powerful tool across all sciences. We have covered a lot of ground today, so let us review the key takeaways. First, converting a Markov chain into a state diagram transforms abstract numbers into a clear visual map of nodes and arrows. Second, we learned that accessibility means there is a valid path of arrows from one state to another. Finally, when two states are mutually accessible, they communicate, forming a two-way loop. You now have the tools to visually analyze complex probabilistic systems. Great job following along, and thank you for watching.